So with that out of the way, we'll go ahead and start. This evening, we have the distinct pleasure of welcoming Dr. Adam Riess to our series. He has many roles here at Johns Hopkins and in the science community. He is a Bloomberg Distinguished Professor, the Thomas J. Barber Professor in Space Studies at the Krieger School of Arts and Sciences, a distinguished astronomer at the Space Telescope Science Institute, and a member of the National Academy of Sciences. In 2011, he was named a co-winner of the Nobel Prize in Physics and was awarded the Albert Einstein Medal for his leadership in the high-Z supernova search team's discovery that the expansion rate of the universe is accelerating, a phenomenon widely attributed to a mysterious, unexplained dark energy filling the universe. The discovery was named by Science magazine in 1998 as the breakthrough discovery of the year. His accomplishments have been recognized with a number of other awards, including a MacArthur Fellowship in 2008, the Gruber Foundation Cosmology Prize in 2007, and the Shaw Prize in Astronomy in 2006. All those accomplishments, we are so glad you are here. Thank you, Adam. Go ahead and take it away.
Okay, well, thank you, Bridget. And you left out the biggest accomplishment, perhaps, which is I was a CTY kid in 8th grade.
That's right, it's where it all started.
So that's right, that's where it all started. It's a pleasure to be here. Welcome to everybody. Let me tell you just a little bit about myself and what I do, aside from those titles. I teach astronomy at Johns Hopkins University. I teach the intro to astronomy, sort of non-majors, what you might call astronomy for poets. And I do research. I do research in cosmology, trying to understand and measure the universe. Across the street from Johns Hopkins University is a building called the Space Telescope Science Institute. It's been there since the late 1980s, and that's the location from which we run the Hubble Space Telescope, which you may have heard of, the telescope that has been in space since 1990. It is also where we will run the James Webb Space Telescope, which is due to launch on December 18th. That is incredibly exciting. It's been in development for 25 years. It's going to be the most powerful space telescope, really telescope in general of all time. It's going to allow us to see deeper into the cosmos and unlock, hopefully, a number of mysteries. So that's what I do in the environment in which I work. Now, I'm going to tell you a little bit at a kind of a basic level about the kind of work that I do and the kind of work that I've done over the last 20 or 25 years that led to this surprising discovery that you heard a little bit about in the introduction. So the title is Supernovae Reveal an Accelerating Universe, and I'm going to tell you a little bit about those things. So, oops, I just hit the wrong button. Let me rectify that. Okay. So when we look out at the universe, it looks static to us. So here is an image of the universe. This is actually the deepest image ever taken of the universe. It was taken with the Hubble Space Telescope's advanced camera. And the way you take a very deep image is you keep the shutter open for a very long time to collect the light of the faintest objects you can see. And so we did that with the Hubble Space Telescope. We kept the shutter open for about a month. We picked a relatively blank area of the sky where you don't see too much activity. And as you slowly collect the photons of light, the very distant objects begin to accumulate in the image, as you see. And the faintest objects that you could see in this image are about 1 trillion times fainter than anything you could see with your naked eye. Now, this is a small patch of the sky. If you took a single grain of sand and you held it out at arm's length, you would cover a patch this size. And yet there are tens of thousands, maybe hundreds of thousands of galaxies in this image. So you can see the universe is just absolutely full of luminous objects. So as I said, it looks like the universe is static because, you know, when you look at it, you don't see anything whizzing around. In this picture, I told you we kept the shutter open for a long time, yet the objects don't look blurry. But that's really a false impression. In reality, the universe is expanding as though it received a big kick that we call the Big Bang. And now the separation between galaxies is growing. You could think of the universe like a giant loaf of raisin bread rising in the oven, and the galaxies are like raisins. And the space between them is actually stretching. It is actually growing. Not that the objects are growing, it's the space between the objects that appears to be growing. So this is a remarkable fact about the universe, something that, you may hear somebody say, oh, the universe is expanding, but it's remarkable to actually think about what that means and to actually think about how would you know that? How do we determine that? And so the way we determine that, and so I describe myself as an observer or an experimentalist. I don't think about the universe so much as I look at the universe. And so how could I look at the universe with a telescope and determine this is true, that it's expanding? And what I do is try to measure how far away the galaxies are from us and how fast they are moving away from us. That's how you measure the expanding universe. So how do we measure how far away objects are? And to think about that, it's useful to first think, well, how do you measure how far away anything is, let's say here on Earth? So there are a number of techniques that we have for measuring distances to objects. One of them is known as parallax. And this is basically when you look at a distant object like this tree, and you measure its position relative to something more distant, like a mountain in the background, and then you can move along some distance that you measure, this is called the baseline here, and measure how that object, the tree in this case, has moved relative to the mountain. That is, you're measuring an angle and you're measuring a length. And if you use geometry, you can then determine how far away that tree is without ever crossing that stream. So that's a powerful technique. Another method that we use here on Earth is the method of lighthouses. So you understand a lighthouse to be a very luminous kind of light. And so when you see one in the distance and it looks very faint, you could tell from how faint the lighthouse is about how far away it is. That's how lighthouses work. They tell us at night how far we are from the shore. Now, it could be a foggy night, in which case your lighthouse would look faint even as you're quite close to it. So we have other tools we use, like fog horns, which it's a similar concept as a lighthouse. It's something that's very powerful, but the strength is diluted over the great distance so that a foghorn from far away would sound very quiet. And another technique we use is what I would call objects of known size. So you see a distant object, it might be a car, it might be a plane, and you have an idea that those are actually quite large objects, but they look small, and that allows your brain to figure out how far away they are from how small they look. In fact, looking at this picture of planes, right, you get the sense that the smaller ones that you see are actually further away. It's not like these are baby airplanes that are, intrinsically smaller and that they're all together. You understand that this shows you the perspective of distant and nearby things. And so this is what we do in the universe. We try to measure how far away objects are, but we don't have quite any of these exact objects. These are all, human-made objects. So we use telescopes and we use what nature provides. And what nature provides is very similar to this lighthouse. It's a kind of star that lives in a galaxy that explodes at the end of its life. And so what you see here is a galaxy, has about 100 billion stars in it. And at some point in its life, one of those stars might explode, like you see here. And when it explodes, it's very luminous. It is a few billion times the luminosity of our sun. And so my particular expertise, the area I study, is trying to measure how far away one of these supernova explosions is when I see one. And we do that by what's called the inverse square law, that the brightness declines as 1 over the distance squared. You could think of it as the light, a fixed amount of it has to go out and cover the area of a larger and larger sphere. So a sphere's area grows as distance squared, and so the brightness has to decline as 1 over distance squared. So the amount of light going through the sphere is always the same. And so if you look at a distant supernova that's twice as far away, it'll look 4 times as faint. If it's 3 times as far away, it'll look 9 times as faint. So I use telescopes and look for these exploding stars, these supernovae, and judge based on its brightness how far away it is. The other aspect of the expanding universe that we can measure from the light of a distant object like a supernova is how the wavelength of light, or the color of the light we see, has been stretched by the expansion of space. And so light travels out like a wave, and the wavelength determines the color of the light. And so if the wavelength is quite small, the waves are compressed, then the light will look blue. But as that blue light leaves the supernova, it travels to us, the universe is expanding, and the wavelengths are stretched by the expansion of space, so that by the time we receive that light, the light looks redder in color than when it left the supernova. This phenomenon is called the redshift. It's a little bit like if you've ever heard of the Doppler shift or experienced that when a car, or maybe a police car with a siren goes by, and you hear that change in pitch as it's coming towards you and away from you. It's a similar idea, except it's not the individual object, the supernova or the police car, that's moving. It's actually, in this case, the fact that all of space is expanding. And so we don't just see, this supernova or that supernova with a blue shift and a red shift. When we look around, we see them all with red shifts because they are all moving away from us. So when we look for these supernovae, what astronomers call standard candles, we use them to measure how far away they are and how fast they appear to be moving away from us. That is, how much expansion of space has occurred across that distance. So going back to that animation that I showed you before, we can now get much more quantitative about this. We can measure the distances and these recession velocities of the galaxies around us, noting that because the universe is expanding, there's more space, there's more grid squares between us and a very distant object than a nearby object. And that's why there's this proportionality, this correlation, if you will, this relationship between how far away something is and how fast it appears to be moving from us. If you double the universe in size, something nearby will move just a little bit. Something far away has to move much more. And so that's why there's a linear relationship between these two. And so this is how we know that the universe is expanding, because when we measure the distances and the velocities, they lie along a line like you see, and the slope of that line tells us how fast the universe is expanding. If the universe were expanding very fast, that line would be very steep. If the universe were expanding slowly, it would be fairly shallow. And that's how we learn about the expansion of the universe. Now, if I could just interject myself into this story for a moment, in my PhD, when I went to graduate school in the 1990s, I worked on improving the measurements of how fast the universe was expanding by developing some numerical techniques that allowed me to figure out, when I saw a supernova explosion, more finely tune how far away it was. Sometimes the supernova you see is actually a faint one, which would fool you into thinking it's further away than it really is. Sometimes we see the supernova light through dust in galaxies, kind of like that lighthouse seen in the fog. And so I developed some numerical techniques that allowed me to tell which were which, so that what was initially a kind of messy measurement of the expansion of the universe became very sharp and clear. So just to tell you a little bit about my path during this time. So I was an undergraduate. I went to college at MIT. So I grew up in New Jersey, but then I went to MIT for my college degree. I studied physics there. And then I traveled not very far at all to Harvard University in the same town where I got my PhD. And then from there, I traveled out. Then I went far. I traveled to the Bay Area of California to do a postdoctoral fellowship at UC Berkeley. And then from there, I traveled all the way back to the East Coast to Baltimore, Maryland, where I am now, to work at the Space Telescope Science Institute on the Hubble Space Telescope, and then to Johns Hopkins University, again, which is just across the street. During that time, when I was working, I met some important people who ended up being very relevant in the work that I do. I met a graduate student named Brian Schmidt when I was at Harvard, and I would end up working with him on a very exciting project with our advisor, Bob Kirshner, who was at Harvard at that time. And we began working on a project to try to measure very distant supernova explosions and learn whether the expansion of the universe was changing over time. Because you realize when you look far away, you're actually looking back in time. It takes the light, in many cases, billions of years to reach us. And so we are actually seeing how fast the universe was expanding in the past. And so a question of the day that astronomers had is, what is the fate of an expanding universe? It's expanding, but what happens next? What happens after that? What happens over time? And asking that question is a lot like the question that Newton asked when he tried to imagine what happens to a cannonball when you fire it from a cannon from a tall mountain. And when he thought about this, he thought, well, the more kick you give it, the greater velocity it has, the further it will travel before it falls back to Earth. And if you give it enough velocity, right, then the Earth curves away and that cannonball goes into what we call orbit, right? And if you give it even greater velocity, then it can leave the gravitational field of the Earth altogether. And so that velocity is called escape velocity. And so the question really was about the universe in an analogous way. Is there enough gravity, like the gravity here on Earth, to pull the cannonball back? In this case, to pull the universe back, it's expanding, but that's just now. Maybe in the future, it would stop expanding and start contracting. Or did the universe have escape velocity from itself? Would it, like the cannonball fired with enough velocity, would it keep expanding and escape its own gravitational pull? Now, that's a strange concept to think about, certainly. And I'm going to throw one more strange concept your way as well. Albert Einstein, was the first to really give deep thought about what the fate of the universe was. And now he realized that all the matter in the universe would act like a gravitational glue, slowing and maybe even halting the expansion of space. However, at the time, he thought the universe was static, like that picture I showed you in the beginning. He didn't know that the universe was expanding. And he found this to be a puzzle, because even if the universe was not expanding, if all the galaxies were just sitting out there, whatever was holding them, once you let go, they would start to collapse and the universe would start contracting because of the gravity of everything pulling together. And so when he struggled with this problem, he realized there was another possibility, that while the gravity of objects is attractive, the gravity of empty space itself could be repulsive. He called this property of the empty space the cosmological constant. Today, we would call it dark energy. And he imagined that the gravity, the attractive gravity from dark matter in the galaxies, was pulling the universe together, but that the repulsive gravity from empty space, what we would call dark energy, was pushing it apart. He thought these two were in kind of a stalemate. However, when astronomers learned in the 1920s and 30s that the universe was expanding, he did away with this idea. He called this actually a big mistake, but that idea has always been around. So how do we learn then about what the actual trajectory is of our universe, whether it's slowing in its expansion or not? And as I said, we look at ever more distant objects and realize there's a time delay. Just like when you talk to somebody across the room, you're not talking to them the way they are now, you're talking to them the way they were a small fraction of a second ago. We are looking at supernovae, which are telling us not how fast the universe is expanding today, but how fast it was expanding in the past. And we look further and further out to look further and further back in time and try to measure if the expansion is slowing down. And so when I began working on this in the mid-1990s, astronomers thought that there were two possibilities. Either the universe was so full of matter, so full of its attractive gravity, that although the universe was expanding, it would start contracting again in the future and end in a kind of a big crunch, the opposite of the Big Bang. Or the universe was very lightweight, that there was not a lot of gravity, in which case the universe would expand forever, like that cannonball escaping the gravity of the Earth. And so we thought we could look at these distant supernovae, these exploding stars, and measure the expansion history of the universe. And so how do we do this? Well, we use powerful telescopes like the Hubble and other telescopes, and we look for a point of light like the supernova that I showed you before, but now here's a very distant one in a distant galaxy. And this is what makes the Hubble Space Telescope so powerful, is it sits above the atmosphere, which normally would blur together the light of a supernova and its host galaxy. And so here is a supernova and its host galaxy seen from the ground with the blurry vision, and then seen with the Hubble Space Telescope with the sharp vision available in space. And so in the late 1990s and early 2000s, I observed many of these supernova explosions, and you see them here at the ends of the arrows. It's the new point of light that appears in a galaxy far, far away. Okay, and so my colleagues and I, the High Z Supernova team, spent a couple of years collecting measurements like this, like the ones that I showed you. And here's a key page from my lab notebook. In 1997, I was analyzing our team's data, thinking that it would tell me that the universe was slowing in its expansion, would tell me how much matter was in the universe and whether the universe would recollapse. And what I saw was really quite surprising, quite shocking, really, was the universe was acting like it didn't have so much matter. More, it was like the matter, it was as though the matter had a negative sign, as though the universe was not decelerating, it was accelerating. I didn't know at first what was going on, and then remembered Einstein's idea that there could be this other possibility, this kind of dark energy or gravity of empty space. And so after looking at the data for a while and with my colleagues, we realized this is what was really going on, that neither of the two stories was right that existed before this work, that the universe was slowing in its expansion a lot or a little. It's actually accelerating. And we now attribute this cosmic acceleration to the universe being mostly in the form of this dark energy, about 70%. And so as Bridget mentioned, this was the breakthrough discovery of the year in 1998. This also was the work that I received the Nobel Prize, shared with my colleagues from the High Z Supernova team. And winning the Nobel Prize is certainly a highlight of any scientist's career. In order to win a Nobel Prize, you have to discover something big, which really means you have to be extremely lucky. And so I'm happy to talk more about that in the rest of this talk. So I'll just conclude with telling you what I do now, which is to follow up this discovery. This is one of those kinds of discoveries that creates more questions than answers. We now know that the universe is 70% in the form of this dark energy, but we don't really understand it at a very detailed level. Our basic physics still struggles to explain and predict what causes empty space to have this kind of background energy with repulsive gravity. And so in trying to get a deeper understanding of the physics of two theories of physics, really, our theory about gravity called general relativity from Einstein, and our theory of the atomic world, what's called quantum theory, trying to understand how these fit together is required to understand and explain this dark energy. And so again, as an observer, as an experimentalist, I go out and look with telescopes and try to better measure what the universe is doing, because it might teach us how physics actually operates in the universe, how gravity and the atom actually work together in some way, in some deeper understanding of physics. And so that's still pretty much what I do to this day. So I think that's a pretty fair introduction. And now I'm happy to just chat with you all if you have any questions.
We have a lot of questions. Thank you for all of that information. I think you had me until about slide 4, and then it started getting really blurry. But I know our students are definitely following along because they have great questions. There's a lot of questions, as you can imagine, about dark matter, dark energy. Has there ever, or do you think we'll ever be able to collect a sample? And what about the relation between that and space-time fabric? I don't know what that means, but I'm sure you do. And just a lot more, like, I know it's unknown, but what do we know, or what could we find out possibly about dark energy?
Right. So the important thing first that I want to say is that dark matter and dark energy are two different things. And we have different evidence that tells us both of them exist. And as I said, that they're different. So dark matter sounds very mysterious, but in many ways it's not. If you're in a room and it's dark in that room and somebody bumps into you, right? You could suspect that there's a person there. You might call them a dark person. But if they don't have light, but they do other things that tell you their presence, then you realize they exist. And so in our case, we look at galaxies with stars whizzing around them, and we see those stars are traveling much too fast. They should just be flying away from those galaxies. There's extra gravitational glue in those galaxies that's holding in those stars, but we don't see light from that gravitational glue. And so we call it dark matter. It's really, another name for it would be extra gravity. Okay. Now, what we strongly suspect, based on a lot of other experiments, is that the form of that dark matter is very likely a particle. You may have heard of particles. There are particles like electrons and protons and neutrons inside an atom. There are many other kinds of particles. They're, obviously very small. You can't see them, but in this case, they don't seem to emit light, and yet they're very common. They actually are about 90% of all the matter in the universe, as far as we can tell. Now, we're constantly doing experiments in laboratories trying to directly detect the dark matter particles. And so far, we have not been able to do that. We believe that dark matter is, the acronym is WIMP, for a weakly interacting massive particle. And that weakly interacting part means just that. They're very difficult to get to light up or show themselves in a laboratory. Now, dark energy is very different. Dark energy is not extra gravitational glue. It's repulsive gravity. It actually pushes things apart, not together. And so that's another case where we see the universe not operating the way you would think things would move around just based on the things you can see. So there's a lot more in the universe than we can actually see. And so there are these sort of this yin and yang, the dark matter and dark energy. One pulls, one pushes. They seem to operate together to give us the universe that we have. We struggle to find them in laboratories because they don't emit light, and they're also both very subtle. The only reason that we know about their effects is they're subtle, but they're common. They make up most of the universe, and so their effects add up when we look at cosmic scales in the universe.
And we did have a question from one of our younger students, and they want to know, what do you think, or what do scientists think happened before the Big Bang?
Well, that's a really good question. First of all, nobody was there that we know of, and so we
Right.
can't really ask anybody. We have very good theories in physics that allow us to run the movie of the universe backwards in time to understand what happened at different parts. It's sort of like saying, if you saw a ball flying across the room and you made a few measurements, you can actually figure out where that ball came from, where it was thrown. You might track it all the way back to, a person or a location. But then your physics breaks down when you try to say, well, who threw the ball and why did they throw it, right? And so our physics is very powerful at connecting the dots of this story to a point. And that point is the Big Bang. But they're not very powerful at telling us what happened before that. We just don't have any data about that. And our theories don't naturally tell us. Now, there are some very speculative theories that make some statements about what came before the Big Bang, but they're quite speculative. They're very difficult to test. Some of those tell us that the universe expands and recollapses from time to time, or that there are other universes that can crash into each other and start a new round of what looks like a Big Bang. But as I said, they're very speculative. We don't have a lot of data that we could even tell you which is more likely right or not. That kind of sort of speculative work is very different than the things. It might sound like what I've been talking about is kind of crazy and exotic too, dark energy and dark matter, but that's like nuts and bolts compared to some of these other ideas.
We have a lot of questions about celestial life and aliens, and what you think it is out there
Right.
in any kind of life forms.
Right. So first of all, anytime you talk about life being out there, you always want to start that conversation with, especially if you don't think about this a lot, about how many chances we get at having life somewhere else. And so in a galaxy like ours, there are about 100 billion stars in it, okay? And we now believe that most stars have one, if not multiple planets, okay? So you're talking about somewhere between 100 billion and a trillion planets in a galaxy like ours. Now, in the visible universe, just what we can see, there are at least 100 billion galaxies. So now you're talking about 100 billion times 100 billion, okay, planets in the visible universe. So then now you ask the question, is there life there? And I would say it would be shocking if there wasn't life in many places in the universe. There are just too many opportunities, too many chances. And as far as we can tell, the conditions on the planets, at least the ones we've been able to see, vary a lot. They might be hot, they might be cold, they might have water, they might have carbon dioxide. So even if you take the view that there are all these planets, 100 billion times 100 billion, and they vary all the possible situations, hot, cold, watery, rocky, everything. Again, it would be surprising. It would be hard to understand that there wouldn't be life over all these places. So I'm a firm believer that the universe is chock full of life, but it's very difficult to make direct connection with that life because the distances involved are so enormous.
What is the coolest thing that you have seen in your years of work in space? What do you think?
Wow. There's so many amazing and exotic things. I'll tell you one thing that just popped in my mind. This might not be the most, but it's one of them, is there are some places in the universe far away from us where there are heavy objects between us and those distant things. And light, when it travels to us, can take multiple different pathways to get to us, so that those distant objects look like when you look at yourself in a funhouse mirror, they're all distorted and bent. But in this case, you can see multiple images sometimes from the distant object because the light can travel along different paths. Just like in a funhouse mirror, you might see a big giant version of yourself on the left side of the mirror and a tiny squishy version of yourself on the right side. And we have actually seen cases where a supernova exploded in a galaxy, and we saw the light from that supernova appear 4 or 5 times. It's only one supernova, but multiple images, and those are delayed with time. And so we might see those events separated by years. And so it's like the movie Groundhog Day, if you've ever seen that, where like you keep seeing the same event over and over, but it's just one event. So we see some pretty cool things in the universe sometimes.
Do you enjoy thinking more about the philosophical implications of your research, or do you prefer the statistical, the scientific side of your field?
Well, that's a great question. I think I love cosmology, this field, because it has so much of both in them, and I really do like both of them. So I like to spend time on the sort of technical details to get the details right. And then when that's all kind of put to bed and in good shape, then I like to think about what it means. And so I like both. I think if I only did the philosophical part, it wouldn't feel real, like I was just dreaming and speculating. And if I only did the technical part, it would feel after a while kind of boring and not that interesting. So I really like sort of both parts.
So I want you to think back on, your time when you were a young CTY test taker and an 8th grader taking the SAT. Did you always know this was what you wanted to do? Has this been your path all along since as far as you can remember?
I would say no. I mean, I didn't know that I was going to these areas, but they kind of picked me in some way. I mean, when I remember sitting down to do the SATs in 8th grade, and I remember that I hadn't yet learned what all the symbols meant. So, there was this thing called pi. I didn't know what that was. And it just kept showing up. So I'd kind of make up a story about it. Like, well, let's sort of say it's a thing, it's a number, and it keeps appearing. And I'll assume it would make more sense if it's always the same number everywhere it appears. And, it's like a puzzle. Like, imagine learning a language is to keep seeing some word and you don't know what it means, but, by context, you might be able to judge. And so that way of puzzling through things was, very natural to me. And I think it's what drew me to math and science, so that, after a number of years of school, I decided that this was the thing that was most interesting to me.
Do you have any recommendations for some of our young astronomers and books that they could read, or websites or blogs they can follow, or apps to look at, just for
Right.
people interested in the field?
Well, you could certainly look at the NASA websites. There are many educational pages on the NASA websites that I think are very interesting. There are some good books. And then I would follow some of the interesting events going on in the news that involve space, like follow the story when the James Webb Space Telescope launches in December. And, stay tuned over the first 6 months or a year to see what the first pictures look like, what they tell us about space. Make it, fun, contemporary, and timely. It doesn't have to be a dry, study of textbooks. It's, science is a very living, breathing subject. We're constantly pushing the frontiers, and, you can follow those stories in magazines and newspapers. Magazines are good too. Pick up a copy of Astronomy magazine or Sky and Telescope magazine. If you know what magazines are, they're paper things that you find at things called stores that used to, I don't know if they still exist, but anyway, they have websites as well, Astronomy and Sky and Telescope.
So with the launch of this telescope on December 18th, is that something that's similar to like a space shuttle launch that people will be able to watch?
Yep, they should. I don't know what the televising schedule is, but it's supposed to launch around 7 in the morning, and it's going to launch on a giant rocket called the Ariane rocket from French Guiana in South America. The telescope traveled on a ship through the Panama Canal. It just made it through and just arrived, and it's being packed back up to fit inside the rocket. And I assume that will be televised at least on the NASA website.
What kind of new discoveries do you think that we're going to be looking for with that telescope?
Right. A telescope is really a capability. Like if you had blurry vision and somebody gave you a better pair of glasses, and they might ask you, what kinds of things do you think you'll figure out and see when you can see better? And it's almost unfathomable how many things you might be able to see and what you might learn from those things. I have some very specific ideas. I want to be able to look in greater detail at stars in some of the nearby galaxies, and better use them to better calibrate this whole process of measuring how far away things are. So other people are planning to look at the atmospheres of planets around other stars and try to start to begin the process of seeing if those atmospheres have the chemicals that are necessary for life, like water and oxygen and methane and carbon dioxide. Other people will be looking at the most distant, really the first galaxies and stars to appear in the universe, and try to figure out basic parts of the story, like which came first, stars or galaxies.
Question, more personal questions. What did it feel like when you won the Nobel Prize? Was it something that you were always hoping and aiming for? Was it something that happened because of the discovery, or what was the thought process?
Right. Well, I mean, it was incredibly exciting and thrilling. I have to say, though, I mean, you don't go into science to win a Nobel Prize. I think you would be crazy to do that. It's so incredibly rare. It would be very unhelpful to go into a field like that. It's not like, I don't know, I guess in sports you might say, I'm going to play the sport to win the Super Bowl or something. That would be much more realistic than going into science to win the Nobel Prize. You need to be very lucky to make a discovery, and then it's less about you than really the discovery and the significance of that piece of work. So I never had any dream or hope of that, until pretty much when it happened.
For our older students that, we just started this new unit at CTY talking about student support. We're focusing on career explorations and resources. So what kind of recommendations would you have for students that know that they want to study cosmology or astronomy, and both? Physics? Right. What advice do you have for them?
Right. Well, there's sort of two parts to it. just like, anything else you learn in life, like maybe you love music, but you need to learn the scales first. And so you can enjoy listening to music you love, and then you need to work on the scales. And so in this case, you could read about cool cosmology and astronomy in magazines and books and the newspaper, but then you need to study basic math and basic physics, because those are the building blocks really before you can sort of make cool discoveries about the universe. It really comes down to learning math, learning about numbers, learning how to work with them and becoming facile with that. Computer programming is very important. That is a basic skill that if you're thinking about anything in the sciences, I would highly recommend learning programming.
What about the universe? Do you think it could eventually decelerate its expansion?
Well, it doesn't look obvious that it would. I mean, after all, it's accelerating now and there's dark energy and it's pushing it apart. We don't really understand enough about the nature of dark energy to rule out that it could actually still collapse in the future. If dark energy actually changes with time, and there are theories that suggest that it should, then that story could change, that the universe could still recollapse. And so I think, it becomes very difficult to make predictions about the future when you don't yet understand at a really basic level the physical properties of these kind of more mysterious pieces, the dark matter and the dark energy.
One of our students has a question, and they said, I can see stars from my friend's house, but not from my own house, but we live in the same neighborhood. Can you tell me why?
Wow, that's quite a mystery, actually. There's a lot of challenge we have with seeing stars in your backyard. One of them is that there's a lot of bright lights, either from your neighbors or from your city, and so that mostly wipes out a lot of the light that you might see. Then it might depend a lot on which direction you're looking, which direction the scattered light is. Something else that might be is when you go into your backyard, some of the lights might be obscured by trees. Another possibility is you're not allowing your eyes enough time to adjust to the dark. And so you step into your own backyard fresh out of the house when your eyes are not yet adjusted and you don't see any stars. And by the time you make it over to your friend's house, walking in the dark, your eyes have dark adapted and now you can see the stars. So, I love puzzles like this, and you should be able to figure this one out.
So have you ever wanted, when you were starting to study math and science and thinking about space, have you ever wanted to go into space? Was that ever something you wanted to do?
Not very much. I mean, space is fascinating to me. The act of going there seems very different than these sort of, like, that almost seems like tourism versus the elegance of understanding, the curiosity. The questions I have won't get answered by me traveling up into Earth's orbit. I need to look through telescopes. I need to work with mathematics. I need to build models and understand the universe. I respect, and I think it's fascinating, the people who go up into space, but it's almost like I said, it's like a different endeavor. Like it's more like being a tourist than the things that I do.
It feels that way, especially now that we have
Yeah, right. People are literally
civilians going
become tourists. You could
into
pay some
space.
money and go up for 10 minutes into low space. And I think that's great. I, again, have more power to the people who want to do that, but that wouldn't scratch the itch I have to understand more about space.
What do you think is the greatest discovery in astrophysics?
Wow, the greatest discovery in astrophysics. My gosh. There are so many great ones. I mean, I still think the discovery that the universe is expanding, which was made in the 1920s. Maybe the most amazing one is the discovery that the other galaxies are outside our own galaxy. So in the early 1920s, astronomers thought that there was only the Milky Way galaxy and that all the little smudgy things that they saw were just clouds of gas and dust in our own galaxy, and that was all there was. And once they learned by measuring distances, as I described in my talk, how far away those smudges were, they realized those were galaxies just like the Milky Way in size, but so far away that they look tiny, and that they were many times the distance to the edge of the Milky Way beyond the Milky Way. And that realization just, it expanded the universe, not like it's expanding in our minds. It expanded it from, as though thinking your one town that you live in is the only town that exists, to realizing, that the Earth is covered with towns. And so I think that, as a cosmologist, those are, to me, the most profound, the ones that really give us a perspective on just how big space is.
Do you think that there's another dimension beyond space?
I don't know. I mean, we know about our 3 spatial dimensions. We know about the dimension of time. There are a lot of physics theories that speculate that there are other dimensions that we don't see or experience. And, so far we don't require it in our physics, but it is an interesting possibility that might ultimately solve some of the puzzles that we have.
Other universes. Do you think that other universes created the Big Bang? Maybe.
Right. So that gets into these more speculative ideas that might be true, but as a scientist, what's frustrating to me is they remain speculations in my mind. Like, I would like to test them. I would like to do an experiment to figure out whether they're true, but we haven't come up with a way to test those ideas yet. But we didn't know how to test a lot of things, decades ago that we now know about. So maybe one of you out there will help us do that. Will, use new powerful facilities, experiments, and, help us learn about whether there are other universes.
I think I have 2 last questions. One, what discovery do you think are we really close to getting to? What are we just need a little more time? What big discovery might we have?
That is a really great question. I wish I knew. That would be the thing I would be working on right now. But I do think, we're getting close to getting a basic understanding of how common planets are and what they're composed of. I think we're getting closer to understanding whether we have figured out everything that the universe is made of, the dark energy and dark matter, or whether there's something else still out there. I think these are a couple things that are big and exciting, but we're getting close to answering.
So we might see those answers in our lifetime, which is good.
Yes.
Okay. Well, one last question, and this is more life philosophical. Do you have any advice for our students that are, like we said, maybe 2nd through 12th grade, but our students that are thinking about college and going on to start their careers? Like, what piece of advice could you give them just about life in general?
Right. I mean, I think the best advice always is, a lot about life when you're young is a search for finding the things that you're passionate about, the things that you really love, the things that you find compelling. And if you find those and you can spend your time on those things, work will never be work. You'll always feel like you're just following your loves and interests, and maybe people will pay you for that. And that's how I've always felt. And, I think the most important thing is to try to figure that out about yourself. What is it that really interests you? What is it that you really love? And try to pursue those things.
That's great. That's very true. Thank you so much. We had over 400 questions. So apologies to those that we did not get to, but Adam, it was amazing to speak with you. This was an amazing conversation, and I'm glad it's recorded so I can go back and try to figure out what you were saying at the beginning. But thank you again for joining us, and thank you to everyone that joined us this evening. We would love to have you back and inspire some fellow CTYers like yourself.
Take care.
Thank you.